Hi, everyone. This is the second lecture for the summer preparation series on probability. Today's topic is set operations. Recall that we talk about a sample space of 10 by 10 or 100 elements. This is a place where we have a subset of people who like chocolate and a subset of people who like peanuts. These are two different subsets. And the entire set of the sample space is 10 by 10 or 100 elements. So each of these cells is called an element. When we talk about probability, we usually talk about conducting an experiment. The experiment is usually about picking an element out at random. So if we have 100 elements and these elements are customers, then we could talk about picking someone out at random. These are some of the probability questions we can ask about this person. Will this person like chocolate? How likely is this person not going to like chocolate? So we can talk about the inverse or the opposite of liking chocolate. We can talk about the probability that this person will like both chocolate and peanuts. And talk about whether this person will like either chocolate or peanuts. These are two very different questions. We'll see. And we can also ask whether this person is going to like peanuts, given that we already know that she or he likes chocolate. Okay. Not, and, or, given are four kinds of questions we can ask about probability, and some of them actually involve two different subsets, right? So the first one is only about chocolate, but the other ones are about chocolate and peanuts. So we're asking questions about the relationships or the combinations, the interactions between two different subsets, and that's why we call these set operations. So these are two different subsets, and we can do operations about them, and that's what we call set operations. There are four different kinds of operations we'll talk about. The first one is called not. Not is also called complement. The second one is called and the formal name of and is intersection. Or is sometimes called union. Given is what we call conditional probability. These are operations for constructing new sets. So every time we use this operation, the outcome of the operation is another set. So we're constructing new sets from existing sets. So our existing sets are those who like chocolate and those who like peanuts. Very typically, you will see Venn diagram being drawn to represent sets. So instead of the pictures I had, usually textbooks have these two circles or three circles of Venn diagram. Each circle represents an event, or no, I'm sorry, a set. And then you can see how these sets overlap. So this is a very common way. So I want you to be able to recognize what a Venn diagram is. And you will see why this is a more convenient way of doing things, because it's just a little time consuming to always draw chocolate versus peanuts. So it's easier if we can just abstract and represent them using just circles. Okay, so I want you to start getting used to this. We talk about the event C, which is liking chocolate. The probability of drawing someone who likes chocolate is 24 out of 100 because we counted 24 cells or squares. And the entire sample space is 100, and that's why it's 24 divided by 100, or 24%. And then we can talk about the event of not C. And the probability of not C is everything outside of this brown region, and that's right here, right? So all these is not C, which is the complement of C. And to figure out not C, we'll just take the entire sample space and subtract it from, subtract 24, which is C, from the sample space. And then we divide it by the sample space, which is 76 divided by 100, or 76%. Okay, so you can see that not C is just the complement, or the rest of the sample space that's outside of the C region. Hopefully you see that's pretty straightforward. And this is what we call absolute complement, which is, if you look at the C region right here, okay, not C will be everything outside of C. So this is the region of 76%. And you can see that in this particular case, the sample space for not C is 100, or this entire region over here. Okay, so we always divide by the size of the sample space. In this particular event of liking peanuts, it's 16 out of 100 people, so 16%. The event of not P is 100 minus 16 divided by 100, which is 84%. So you can see right here, lots of people who don't like peanuts, which I don't understand because I love peanuts. But clearly I have a minority because only 16 out of 100 likes peanuts in this particular sample space. So again, not P is another form of absolute complement. And it's this region that's outside of the P circle. Now, in addition to absolute complement, there is also something called relative complement, which is when we talk about not P, we're talking about not P in relation to region C. This is where the relative comes from. So we want to look for C, okay, those who like chocolate, but we want to specify we only want those who like chocolate who also do not like P. Okay, so in this particular case, the visual is really helpful because we can look at the C people. It's right here. Okay, but then there's a small percentage of them that like P. So if we want to include only those who do not like P, we have to take this particular area out. And you can count how many there are. 1, 2, 3, 4. There are 4 of them. So what we need to do is we need to specify this region, C not P. And what we can calculate is we can take the probability of C and we can minus the probability of the way to represent it mathematically is C minus P, or C backslash P right here. So these are the 2 different ways to write them. You see these in textbooks a lot. And C backslash P is basically 24, which is this big region, the region C, but we want to subtract the overlap, which is this little area, from it, and that's how we get 20 divided by 100, or 20%. So 20% is this yellow region that is people who like C, but it's like, excluding this area of people who like P. So again, this is how we write it mathematically, C minus P, or C backslash P, and on Venn diagram, this is how we represent it. It will be the C circle outside of the P region. Same thing. Another example of relative complement is P not C. So those who like P but do not like chocolate will be this region. And we will write it as P minus C, P backslash C. And then we'll take the entire region of P. Okay, so this entire region is 16. But then the overlap over here is 4. So 16 minus 4 is 12%. Or divided by 100 is 12%. P minus C, or P backslash C, refers to this region over here. All right, so that is not or complement. And now we're going to move on to our next experiment, which is picking someone at random, and we want to see if this person will like both chocolate and peanuts. So this is what we call the AND operator. It's also called intersection. So we're looking at the intersection between C and P. And that's this little region over here. We've seen it quite a few times, and it's 4. And we represent this relationship, this intersection relationship, using this upside down U symbol. So it formally represents this region. And how do we know the size of the region? Well, we count the number of cells. So usually this has to be estimated empirical. You have to go out and ask people. And, or, you know, these numbers will be given to you at exams or quizzes or questions. Usually people will have to give you this number, or they'll give you other numbers so you can calculate this region. But right here, we can just look at it and we actually know. We count 1, 2, 3, 4, and we know it's 4 out of 100, and so it's 4% of the sample space. So it's a very small portion of the sample space that actually likes both chocolate and peanuts. So that's this little region over here on the Venn diagram, and that represents the customers who like both chocolate and peanuts. So you can see that, you know, this circle is 24, this circle is 16, and this little region is 4. And that's the group of customers who might want to buy Reese's peanut butter cups from you. Okay, the next experiment is to pick somebody at random to see if this person will like either chocolate or peanuts. Or is also called union. And union is a lot more inclusive across these two subsets. So we have these two subsets, 24 and 16, or means that you only need to like one of these products. You don't have to like both products. So anyone in either region can be included. So we should get a much, much bigger number. So what you want to do is you want to count this region. It's called C or P. And what we can do is we have these two numbers. We can add them up, except that in this particular case, there is a little bit of an overlap. So we have been talking about this overlap, which we now know is called intersection. Okay, or and, right? So this is the and region of 4. And at this area is double counted. It's counted twice, because when we count C, we include this region. When we count P, we also include this region. So we count it twice. So what we do is when we add 24 and 16 up, we want to subtract 4 out of this overlap. Has to be taken out. And so we get 36% over here. Okay, so this is how we represent it formally in the textbook. The area is the symbol is the U-shape symbol. It's called union, C union P, is everything that's covered by either circle on the Venn diagram. So customer who likes either chocolate or peanuts, you know, usually in the textbook you will see representation like this. You count 24, 16, and minus 4 in the middle. Lastly, we're going to look at an experiment that's about the probability of people liking peanuts, given that we already know that she likes chocolate. So this is on the condition that we already know that this person likes chocolate. This is what we call conditional. And the symbol for conditional is this bar, this vertical bar over here. So we read this as P given C. Okay, so in this particular case, C is the condition And P is what we want. So we want those who like peanuts. So that would be this area. Given, so these are everybody who likes peanuts, but we only want those who like peanuts that we know already like chocolate. So it'll be this region, okay, is everybody who likes chocolate. Out of all these people who like chocolate, we want those who also like peanuts. What's the probability? So again, we're looking at this intersection over here. However, the new thing here is that we're only dividing it by 24, not 100 anymore, because we only want those who we already know like chocolate. Okay, so this is the probability of picking someone who likes peanuts, which is the number 4, given that we already know that this person likes chocolate. So given this smaller sample space of 24, not 100 anymore, we want to limit to only those people who we know for sure that they like chocolate. Out of those people, only 4 of them like peanuts. So 4 divided by 24 gives us 16.7%. So this is how we represent it formally. P given C is this little region. Okay, so this is our new sample space, and also out of this new sample space, we're looking for this area. So this is 4 divided by the new sample space of 24. Okay, so this number 24 over here, you know, the denominator has to be the size of the sample space. The sample space used to be 100, but now with the conditional over here, the size of C will become the new denominator. Conditional probability is directional. So when we say P given C, C is the sample space, so we divide it by 24. Okay, so this region divided by 24. However, when we talk about C given P, then P will be the new sample space right here. And C given P, because P is the new sample space, 16 is the size of the new sample space. So C given P will be 4 divided by 16, or 25%. So that's different from this number, which is 16.7. This is P divided by C. So even though we're looking at the same region over here, because the sample space has changed, whether it's C or P, you will get a different probability. So again, to summarize, conditional probability is directional. X given Y is different from Y given X. The condition is the number that you use as the denominator. So X given Y will be the intersection, which is over here, divided by the probability of Y. However, when you have to calculate Y given X, you will need to use X as the sample space, and the probability of that will be the denominator. The numerator is still the intersection, X intersection Y. Okay, so that's the overlap, that little region of 4 is this intersection, but the numerator, the denominator will change depending on what's your sample space over here. Will change depending on your condition. So this is your condition. If you work for Netflix, this will be a very common question that you have to answer as a manager. So given that a customer, Scarlett, watched season 8 of Game of Thrones, how likely is she going to watch season 9? Okay, so hopefully you see that this is something that the Netflix recommendation system is trying to solve all the time. And we can express it as the probability of season 9, liking season 9 given season 8. So now this is the condition, this is the sample space, right? So we're not talking about all of the customers, we're only talking about customers who watched the season 8. How likely is this person going to watch season 9? So again, this is something that's very useful for Netflix, and hopefully you can imagine that Netflix uses a lot of conditional probabilities in their business operations. So again, this is the new sample space, season 8. A lot of times you will also see the probabilities as organized or presented as a joint probability table. It's just a very easy way to summarize the relationships among all these different numbers that we're being seen. And this is actually the basis of Bayesian statistics, which is very popular right now. It's used in a lot of data analysis. But it's just a very simple summary of all the numbers that we have seen. Okay, so let's start with A. So letter A over here is this little region, the intersection, and that is the intersection of P and C. Let me change the color of my pen so that it's easier to see. So you can see that the rows are P and not P, and the columns are C and not C. So when we have both P and C, we're talking about intersection, and that's this region right here. So that's A. If we're talking about C but not P, so this is your relative complement right here, and that would be the B region. So this is the area that's outside of the intersection. So this is your C minus P, or C backslash P is this B region. When you add these two together, A and B, when you add them together, then you get your probability of C. So the entire C circle is the subtotal for this column, the C column. Okay, so, and then we also have the column of not C. So not C would be, this region is not C, but it's inside of P. So that's this region over here. Okay, and then you have D, which is not C and not P. So it's outside of P and it's outside of C. So it's everything else in the sample space is D over here. And then if you add C and D up, you will get everything that's not C. The probability of not C will be C plus D. You also see that when you add A and C up, you get the probability of liking peanuts. You add B and D up, you get B over here, and D, you will get the probability of not liking peanuts. And then you add A, B, C, D all together, you will get both the C and P circles plus everything else in the sample space. So that is our total right here. So here is the joint probability table. Again, it's the same thing that we saw on the last slide, but now we're adding four more calculations. So the conditional probabilities can be calculated by dividing A. So this is the first one, P given C is A. So this intersection. So if you go back to look at the formula, that this is exactly what it does. It's the intersection divided by the probability of C. So the new sample space, right? So this condition over here, we want this probability, it's right here. And then the probability of P and C, the overlap is over here. So we will take A and divide it over here. So this is the probability of P given that we already know that the person also likes chocolate. So P given C. Similarly, you can do P given not C. You will just take C divided by C and D. Over here, you can calculate the probability of liking chocolate, given that the person also likes peanuts. So it'll be A divided by A plus C right here, because this is the probability of P. So you would take this number A and divide it by A plus C. You will get C given P. And then you can take B and divide it by the subtotal. So remember, A plus C, B plus D are subtotals for these two rows. So this is P. Okay, so P, the probability of P is the subtotal is the sum of these two numbers. You get probability of P. Probability of not P is the total of B and D. So B and D plus together, we'll get these. And then this total, the subtotal, if we use it as a denominator and we take B as the numerator, then we'll be able to calculate C given not P. So you will get, with these divisions, you will get these conditional probabilities. You can also take these three cells, add them together, A plus C plus, actually it should be A plus B plus C will be the area of P or C. Okay, so that's it. And now let's go to the Google Sheets demonstration to see an example of how we can actually represent this in a spreadsheet. Again, this is the Google Sheet file where we have all our demonstrations. So you want to make sure you go down here and look for the demonstration that we are focusing on right now. And we already seen S1 Pro. Today we're going to go over S2 Set. You want to click this. You can see that we have a data set of 100 people. Okay, so these are the elements, and now they're represented as 100 rows. So if you go down, you can see 100 customers. And we recorded whether they like chocolate or peanuts. You see a lot of no's here, but sometimes you see a Y. Okay, so Y is yeses. See, this is the column of customer who like chocolate, and this is the column of people who like peanuts. And then these are your A, B, C, and D. So A, B, C, and D, and we can calculate each of these regions using operations. So A is both C and P. So this is the intersection. So what we do is we can actually use, in Excel, we have this AND operator. It's called and that is, you already know what it is. It is the intersection between the first item and the second item. Okay, so we want AND of both liking chocolate, so the first one, and C, right, and P. We also want the second one to be yes. So we want the intersection of both yeses. And so we use and then we drag down and apply the formula to all these rows. So now we get a bunch of trues and falses. This is true because both of them are Y. This one is false because only the first one is Y, the second one is no. So the answer to this AND operator is false. Okay, so we apply that going all the way down. Okay, so we'll be able to see we have another true here. So just look at the numbers. So this is true because both of them are Y. See, all the other ones are either, the no-nos, it's false. YN is no's, and Y is false. Okay, so we have a bunch of true and false, and this cell, okay, so I labeled it as A, and the cell number 4 is actually calculated by counting this D column, D2 to 101. So this entire column, I only select the areas, the cells that have values in it. We want to count how many of them are trues. Okay, it's true that C and P are both yeses. Then it counted 4 for me, and that is exactly what we saw in the lecture, number 4. Okay, so A is 4. And then B is 20 because we also counted this column. So this column, C not P, is again an AND operator, but it's AND is the first one is yes, the second one is no. Okay, so we did these. We want to find cases where C is yes and P is no. And then we did all the logical, verifications. And then we counted up how many of them are true. And we counted 20 over here. So A is 4 and B is 24. And they add up to, so this one is really just adding these two up, 4 and 20. But I wanted to do it in a different way. So I want to show you that the subtotal for this column is really just the probability of C, like chocolate, which is column B. Okay, so this column, I'm counting how many Y's there are, how many people like chocolate. So I just go down this column and counted Y's, and I counted 24 of them. So we have 24 people who like chocolate, and that is the total of 4 and 20. You see that? So this is the subtotal. So the column, the probability of C is right here. The probability of C is 24, and that is equal to the sum of these two numbers. Now, P given C is calculated by taking the value of A, which is the cell, divided by the subtotal of the column, which is this cell. So 4 divided by 24, or 16.7% here. We also calculated C. Okay, so the value C is P. This is over here is the probability of liking peanuts but not chocolate. So we want to look at those who have Y here but no in the second column. So we use this formula using the AND operator. We want Y from the first column and a no from the second column. So we got a lot of falses, but we have some trues. And this is our orange region, which is letter C over here. And we just count how many true values there are. And we counted 12. And then the last one is we're looking for not P and not C, which is we want to know from this column and we want to know from the peanuts column. We want both of them to be no. So we have an AND operator here. And again, we have a lot of falses and trues, and we counted the number of trues from this pink column, and we counted 64. And that gives us, this is counting the number of no's from the C column, and we counted 76, and that actually is exactly 12 plus 64. Okay, the same thing over here, the probability, the subtotal for A and C is 16, and 16 is actually the number of people who like peanuts right here. So 16 is what we counted from the peanuts column, but it also is exactly 4 plus 12. Okay, those who do not like P is we counted no's from the peanuts column, and that number again maps is exactly 20 plus 64. So the total is 100, okay? And you can also calculate the probability of C given P and C given not P, and you will see that these 4 conditional values are all different. So, because they're all calculated using different values. That's it. So this is a picture of the table, the joint probability table from the lecture. So I want you to see that how this table is actually calculated in practice. how these numbers are put together from a data set. Okay, it's nice to look at the data set because you get a very detailed view of the mechanics underlying all these probabilities. But there's a reason why your textbook usually don't use these, because it's a lot of tables, a lot of space, and it's a little tedious to see everything. So eventually, and it's only 100 records, and it already looks a little, tedious. And what if you have a sample of 5,000 people? What if you have 1 million people, right? So you're not going to be able to represent everything using a table. So, and also just formally, it's more efficient and easier to understand if we just use notations. So if we want to talk about the elements of a sample space of a set, so this is the set C, we usually would just use these curly brackets. We put the elements, we list them inside the curly brackets using commas to separate them. And that would be how we list the elements within this set, okay? And the set of P is usually represented using curly brackets and commas and these values to list each one of these elements. Okay, so see, like this is 1, 5, 7, 10. It's because the first element likes peanuts, the fifth element likes peanuts, the 7th element like peanuts, and the 10th element likes peanuts. Okay, so we skip the ones that are no. So the subset, the sets only include those who meet the that are consistent with the name of the subset, right? So we skip over all the no's when we list them using the symbol. Okay, now we're going to end this lecture with an exercise. I will give you the exercise here, and you should take 10-15 minutes to figure this out before you look at the solution. But as we said before, the solution is already on the Google Sheets. It's on a hidden sheet, so you can always check your answers. But before you do that, I want you to work on this on your own. So here's a data set of 20 houses in the Williamsburg region in 2 different zip codes, 23185. So you see this first set over here is a bunch of houses in the first zip code. I need a different color. So these are 23185 houses. There are 12 of them, and then we have 8 in 23188. And we also recorded whether the price went up or down. So some of them went up, some of them went down. So you have these 20 records as well. Okay. And with this sample, we want you to calculate the probability that price goes up. So what's the probability that price goes up? How will you represent that using all the symbols that we talk about, and how would you estimate that? We want you to calculate the probability that price goes up, given that the house is located in the zip code 23185. What's the probability the house is located in 23188, right? So what's the probability that it's in this region? So by the way, this is where the Mason School is. Given that the price went down, what's the probability that this house is located in the second zip code? What's the probability that the house price goes up that is not in 23188? What is the probability the house is located in either 23188 or 23185? What's the probability that a house price goes up or it's located in 23185? So go ahead and work on this exercise and see how well you do. If you had a good understanding of the lecture, this should be pretty straightforward. Again, the solution is in Google Sheets, and it's on this S2 Set Key tab. Good luck. And there are more practices on Khan Academy. So this is from our course website. You can see the lectures, the lecture 1, all the lectures that we have seen already, but I also have links to the practices. So these are Khan Academy practices. They're pretty straightforward, and you click on the links, you'll be able to complete these quizzes. They're automated. You can see right away whether you got the answer correct or not. All right. There's also a short animation about conditional probability by Harvard's Statistic 110 course. It's known as Bayes' rule, but it's basically the joint probability table and the conditional probabilities that we have looked at. So it's actually quite well done. So I encourage you to take a look at it. Just another way to reinforce the ideas. All right. Have fun, and we'll see you at the next lecture.